Throughout history, certain individuals have shaped the way humanity perceives and understands the world. One such figure is ALHAZEN, known in Arabic as Ibn al-Haytham. A pioneering scientist of the medieval Islamic world, ALHAZEN revolutionized the fields of optics, mathematics, and the scientific method. His work laid the foundation for modern physics and greatly influenced later European scientists during the Renaissance. Despite living in a time when philosophical speculation dominated scientific thought, he emphasized empirical observation and experimentation, setting a new standard for scientific inquiry. His legacy remains integral to the history of science, and his contributions continue to inspire scholars across disciplines. Born in the 10th century during the Islamic Golden Age, ALHAZEN lived in a period of remarkable intellectual flourishing. This era saw advancements in astronomy, medicine, engineering, and philosophy, driven by scholars who preserved and expanded upon the knowledge of earlier civilizations. Within this environment, ALHAZEN developed a keen interest in the nature of light and vision, ultimately producing groundbreaking theories that would challenge prevailing understandings. His most famous work, Kitab al-Manar, the Book of Optics, transformed the study of vision and light, introducing ideas that were centuries ahead of their time. One of ALHAZEN's most significant achievements was his refinement of the scientific method. While ancient Greek philosophers, including Aristotle and Ptolemy, relied heavily on logic and reasoning, ALHAZEN insisted on systematic experimentation. He argued that theories must be tested through observation before being accepted as truth. This empirical approach laid the groundwork for the modern scientific process, influencing scholars like Roger Bacon, Johannes Kepler, and Galileo Galilei. By prioritizing experimentation over mere speculation, he reshaped the way knowledge was acquired and verified. In addition to his work in optics, ALHAZEN made substantial contributions to mathematics. His research in geometry and algebra allowed him to solve complex problems involving light and lenses. He studied the properties of reflection and refraction, developing principles that would later influence the design of optical instruments, such as telescopes and microscopes. His mathematical precision and analytical approach made his findings remarkably accurate, demonstrating his ability to merge theoretical concepts with practical applications. ALHAZEN's contributions extended beyond the scientific realm. He also engaged in philosophical discussions about the nature of knowledge. He argued that human understanding should be based on evidence rather than tradition or dogma. This perspective was radical in an age where many intellectual debates were dominated by adherence to classical texts. His insistence on verifying claims through direct observation challenged long-standing beliefs, encouraging a more dynamic and progressive approach to scholarship. Despite his immense contributions, ALHAZEN's work was not widely recognized in Europe until centuries later. His manuscripts were translated into Latin during the 12th and 13th centuries, influencing key figures of the Renaissance. His impact on Western thought can be seen in the works of thinkers like Leonardo da Vinci and René Descartes, who built upon his theories of vision and perception. The translation of his works played a crucial role in the revival of scientific inquiry in medieval Europe, bridging the gap between ancient and modern knowledge. Beyond his intellectual achievements, ALHAZEN's life story reflects the struggles faced by many great thinkers. At one point, he was tasked with an ambitious project to regulate the flooding of the Nile River. But upon realizing the impossibility of the endeavor, he feigned madness to escape the wrath of the ruling caliph. This episode highlights both the dangers of intellectual pursuits in politically unstable times and the resilience required to continue scientific work under difficult circumstances. His eventual retreat into scholarly isolation allowed him to focus on writing and experimentation, leading to some of his most influential discoveries. ALHAZEN's approach to science continues to be relevant today. His insistence on observation and experimentation as the foundation of knowledge parallels modern research methodologies. In fields such as physics, engineering, and medicine, his principles remain fundamental. By emphasizing the importance of empirical evidence, he contributed to the evolution of science as a disciplined and methodical pursuit. His work serves as a reminder that scientific progress depends on curiosity, rigor, and the willingness to question established ideas. Despite the passage of centuries, ALHAZEN's name remains significant in scientific discourse. His pioneering studies on light, vision, and optics have earned him the title of the father of modern optics. His influence extends far beyond his own time, impacting generations of scholars who have built upon his discoveries. The recognition of his contributions highlights the interconnectedness of global scientific traditions and the importance of preserving and celebrating knowledge from diverse historical periods. The era in which ALHAZEN lived was one of immense intellectual and scientific advancement. Known as the Islamic Golden Age, this period, spanning roughly from the 8th to the 14th century, saw the flourishing of knowledge across disciplines such as astronomy, medicine, mathematics, and philosophy. Scholars from different cultures and backgrounds contributed to an unparalleled exchange of ideas, making cities like Baghdad, Cairo, and Cordoba centers of learning and innovation. This intellectual renaissance was fueled by the patronage of rulers who valued knowledge as a means of governance, technological advancement, and cultural enrichment. A key factor behind this surge in scholarship was the establishment of the House of Wisdom, Beit al-Hikmah, in Baghdad during the reign of the Abbasid Caliph Harun al-Rashid in the early 9th century. This institution functioned as a grand library, a translation center, and meeting place for scholars from diverse backgrounds, including Persians, Arabs, Greeks, and Indians. Greek texts on philosophy, medicine, and science, which had been lost to much of Europe during the decline of the Western Roman Empire, were systematically translated into Arabic. The works of Aristotle, Ptolemy, Euclid, and Galen were not only preserved but critically analyzed and expanded upon. One of the most remarkable aspects of the Islamic Golden Age was its emphasis on interdisciplinary knowledge. Scholars did not confine themselves to a single field. They often studied multiple subjects, seeking a comprehensive understanding of the natural world. For instance, Al-Khwarizmi, a Persian mathematician, developed algebra while also working on astronomy and geography. Similarly, Avicenna, Ibn Sina, a contemporary of ALHAZEN, was a physician, philosopher, and scientist whose medical texts would be used in Europe for centuries. This approach to learning laid the groundwork for future scientific methodologies, encouraging cross-disciplinary innovation. During this period, advances in mathematics and astronomy were particularly significant. The decimal numeral system, which originated in India, was refined and introduced to the wider world through Arabic scholarship. Mathematicians like Al-Khwarizmi formalized algebraic principles, while others improved trigonometry, enabling more precise astronomical calculations. Observatories were established, and detailed star maps were created, refining Ptolemaic models and questioning long-held assumptions about celestial motion. These achievements would later influence the work of European astronomers, such as Copernicus and Kepler. Medicine also saw significant progress, with scholars like Al-Razi, Rhazes, and Avicenna writing comprehensive medical treatises that classified diseases, described surgical techniques, and laid the foundation for hospital-based medical practice. Their methods of observation, diagnosis, and treatment were far ahead of their time and remained authoritative for centuries. Medical institutions in cities like Baghdad and Cairo became models for later European hospitals, with their emphasis on specialized departments, systematic training, and ethical medical practices. The intellectual atmosphere of the Islamic Golden Age was also deeply connected to advancements in engineering and practical sciences. Innovations in mechanics, hydraulics, and optics led to the development of intricate machines, irrigation systems, and architectural marvels. Engineers like the Banu Musa brothers designed sophisticated automata, water clocks, and early programmable devices, demonstrating a remarkable understanding of mechanical engineering. These inventions, while often created for aesthetic or entertainment purposes, showcased a deep comprehension of physical laws and laid the groundwork for later developments in automation. Trade and cultural exchange played a crucial role in the dissemination of knowledge during this period. The vast Islamic empire spanned from Spain to India, encompassing diverse civilizations with unique intellectual traditions. Merchants and scholars traveled extensively, carrying manuscripts, scientific instruments, and ideas across borders. This movement of knowledge was not limited to the Islamic world. Through interactions with Byzantine, Indian, and Chinese scholars, new ideas and technologies were integrated into scientific discourse. Paper, which was introduced from China, revolutionized the production of books and greatly enhanced the preservation and distribution of scholarly work. Despite its immense achievements, the Islamic Golden Age was not without its challenges. Political instability, internal conflicts, and the eventual decline of the Abbasid Caliphate created obstacles to intellectual progress. The Mongol invasion of Baghdad in 1258 led to the destruction of the House of Wisdom, marking a significant setback for scientific inquiry. However, by this time, much of the knowledge produced during this era had already spread to Europe, where it would later contribute to the Renaissance and the scientific revolution. The legacy of the Islamic Golden Age is evident in many modern scientific and cultural developments. Many Arabic scientific terms, such as algebra from al-Jabr and algorithm from al-Khwarizmi, remain embedded in the language of mathematics and technology. Moreover, the methods of inquiry, systematic experimentation, and emphasis on evidence-based reasoning established by scholars of this period continue to form the backbone of modern scientific practice. The life of ALHAZEN began in the city of Basra, a prominent intellectual and commercial hub in present-day Iraq. He was born around the year 965 CE, at a time when the Islamic world was experiencing an unprecedented flourishing of knowledge. Basra, situated near the Persian Gulf, was not only a vital trading center, but also a place of learning, where scholars engaged in discussions on theology, philosophy, and the sciences. The city's rich intellectual atmosphere played a crucial role in shaping ALHAZEN's early education and igniting his passion for knowledge. From an early age, ALHAZEN displayed an insatiable curiosity for understanding the natural world. He was drawn to the study of mathematics, astronomy, and philosophy, subjects that were highly regarded in the scholarly circles of his time. Unlike many of his contemporaries, who often accepted the teachings of ancient scholars without question, ALHAZEN developed a critical approach to learning. He believed that true knowledge could only be attained through careful observation, analysis, and verification, an outlook that would later define his scientific work. His early education was rooted in the classical traditions of Greek and Persian scholarship, which had been preserved and expanded upon by Arab intellectuals. He studied the works of Aristotle, Euclid, and Ptolemy, gaining a strong foundation in logic, geometry, and the principles of natural philosophy. However, rather than accepting these teachings at face value, he sought to challenge and refine them, recognizing that some of their explanations were based on flawed reasoning rather than empirical evidence. One of the most influential subjects in ALHAZEN's education was mathematics. He was particularly fascinated by geometry and its applications to the study of optics and physics. He immersed himself in the writings of Greek mathematicians such as Euclid and Apollonius, carefully analyzing their theorems and principles. Over time, he developed his own mathematical techniques that would later allow him to make groundbreaking discoveries in the behavior of light and vision. In addition to mathematics, ALHAZEN also studied astronomy, a field that was deeply intertwined with mathematics in the medieval Islamic world. Astronomers of his time were engaged in refining the Ptolemaic model of the universe, developing more accurate methods for predicting celestial movements. ALHAZEN was particularly interested in the inaccuracies of Ptolemy's planetary system and would later critique some of its fundamental assumptions. This early engagement with astronomy laid the foundation for his later work in optics, as both fields required an understanding of light and its interaction with different surfaces. The philosophical and theological debates of his time also had a profound impact on ALHAZEN's intellectual development. He was exposed to discussions on the nature of reality, the limits of human knowledge, and the role of reason in understanding the universe. While deeply respectful of religious traditions, he maintained that scientific inquiry should be based on reason and empirical evidence rather than reliance on authority. This perspective set him apart from many scholars who prioritize theological interpretations over rational investigation. ALHAZEN's reputation as a scholar began to grow as he advanced in his studies. He earned recognition for his sharp analytical mind and his ability to apply mathematical principles to practical problems. His fame eventually reached the rulers of the Fatimid Caliphate in Egypt, who invited him to take part in an ambitious engineering project. The Caliph had tasked him with devising a system to regulate the annual flooding of the Nile, a problem that had challenged engineers for centuries. This invitation marked a turning point in his life, drawing him away from Basra and into the political and intellectual landscape of Cairo. Although his attempt to control the Nile ultimately failed, the experience further refined ALHAZEN's understanding of physics and engineering. The project exposed him to practical challenges that theoretical knowledge alone could not solve. He realized that true scientific progress required direct experimentation, a lesson that would become central to his later work in optics. The setbacks he faced in Egypt did not discourage him. Rather, they strengthened his resolve to pursue knowledge in a more systematic and empirical manner. After the failure of the Nile project, ALHAZEN withdrew from public life and devoted himself entirely to scholarship. He spent years in seclusion, carefully studying the nature of light and vision. It was during this period of intense research that he formulated many of his most significant theories, including his groundbreaking work on optics. His ability to transition from a failed engineering project to a revolutionary scientific career demonstrates both his resilience and his commitment to intellectual inquiry. As ALHAZEN's reputation as a scholar and scientist grew, word of his expertise spread beyond the borders of Basra. His proficiency in mathematics, engineering, and the natural sciences eventually caught the attention of the Fatimid Caliph of Egypt, Al-Hakim Bayamar-Allah. The Caliph was known for his patronage of scholars and his interest in scientific endeavors, and he had a grand vision for one of the most significant geographical and economic challenges in his empire, the annual flooding of the Nile River. This unpredictable natural phenomenon brought both prosperity and destruction, providing fertile soil for agriculture while also causing devastation to settlements. ALHAZEN, ambitious and eager to apply his knowledge to practical problems, accepted the Caliph's invitation and traveled to Egypt. Upon his arrival in Cairo, he was presented with the challenge of devising a system to regulate the flow of the Nile. The task was immense, as no known method had succeeded in controlling the river's seasonal inundations. The ability to tame the Nile would not only enhance agricultural stability, but also increase the empire's economic strength by ensuring a consistent food supply. As he began his studies, ALHAZEN examined the geography of the Nile and the surrounding landscape. He reviewed ancient texts from Greek, Roman, and Egyptian engineers, analyzing their previous attempts to manage the river's waters. He also conducted his own observations, measuring water levels, analyzing the behavior of currents, and assessing the structural integrity of existing irrigation systems. His findings revealed the complexity of the challenge. Any artificial intervention could have unintended consequences, potentially causing greater damage than the floods themselves. ALHAZEN devised a plan that involved constructing a massive dam to regulate the river's flow. His design proposed a controlled release of water, allowing excess floodwaters to be stored and gradually distributed to agricultural lands. However, as he delved deeper into the project, he realized that the scale and cost of the endeavor far exceeded what was feasible with the resources and technology available at the time. The idea of building such an ambitious structure was beyond the engineering capabilities of the era, and the unpredictable nature of the Nile's flood cycles made precise regulation nearly impossible. Despite his determination, ALHAZEN ultimately concluded that the project was doomed to failure. He faced a difficult dilemma. Abandoning the task meant disappointing the Caliph, a ruler known for his unpredictable temperament and harsh punishments. Al-Hakim, often regarded as eccentric and at times ruthless, did not tolerate failure easily. Fearing for his safety, Alhazen made the drastic decision to feign madness, a strategy that would allow him to escape the wrath of the Caliph while preserving his own life. His act of insanity was convincing enough to spare him from execution, but it led to years of forced isolation. To avoid suspicion, he lived under self-imposed house arrest, retreating from public life and disappearing from courtly affairs. Although this period may have seemed like a setback, it ultimately became a turning point in his intellectual career. During his seclusion, Alhazen had the opportunity to immerse himself fully in scientific study, free from the distractions of political obligations and engineering projects. In the quiet solitude of his refuge, he turned his attention to the study of light, vision, and optics, subjects that had fascinated him since his early years. He conducted experiments on how light traveled, how it was reflected and refracted, and how the human eye perceived images. This period of intense research led him to develop some of his most revolutionary theories, many of which would later be compiled into his seminal work, Kitab al-Manar, the Book of Optics. Though Alhazen's time in Egypt began with failure, it ultimately set the stage for his greatest scientific contributions. His experience with the Nile Project reinforced his belief in the importance of empirical observation and mathematical precision. It also underscored the limitations of theoretical knowledge when faced with practical engineering challenges, pushing him to refine his approach to problem solving. Instead of relying solely on inherited wisdom, he embraced experimentation as the true path to discovery. Years later, after the death of Caliph al-Hakim, Alhazen was able to return to scholarly life without fear of persecution. His name was not forgotten, and his reputation as a thinker and scientist remained intact. Although he never returned to large-scale engineering projects, his encounter with the Nile had shaped him in profound ways. He emerged from his seclusion not as a failed engineer, but as a visionary scientist whose insights into the nature of light and optics would redefine the course of scientific history. The period of forced isolation that followed Alhazen's failed Nile project proved to be the most productive phase of his intellectual life. Confined to solitude, he turned inward, redirecting his focus from grand engineering ventures to the fundamental principles of nature itself. While many scholars of his time relied primarily on philosophical reasoning and inherited wisdom, Alhazen took a different path, one that would revolutionize scientific inquiry. He embraced direct observation and structured experimentation, laying the foundation for what would later be known as the scientific method. At the heart of Alhazen's approach was the belief that knowledge must be verified through experimentation rather than accepted based on authority alone. He rejected the idea that ancient texts, whether from Aristotle, Ptolemy, or any other revered figure, should be considered infallible. Instead, he argued that all theories must be tested under controlled conditions, their results meticulously recorded and analyzed. This perspective marked a radical departure from traditional scholastic methods, which often prioritized logical argumentation over empirical proof. One of his most significant contributions was his structured methodology for conducting experiments. He insisted on forming hypotheses, designing controlled experiments, and analyzing results to confirm or disprove initial assumptions. This approach prefigured the scientific practices that would later become standard in the Renaissance and Enlightenment periods. Unlike many of his predecessors, who often relied on speculative reasoning, Alhazen built a systematic framework for testing theories, a process that would shape modern science for centuries. His emphasis on empirical evidence extended beyond mere observation. He meticulously documented his findings, recognizing that knowledge should be systematically recorded and communicated. He wrote extensively, ensuring that future generations could replicate his experiments and verify his conclusions. This dedication to documentation set a new standard for scientific discourse, transforming it from an isolated pursuit of knowledge into a shared and cumulative endeavor. One of Alhazen's key insights was his realization that perception could be deceptive. He understood that the human mind is prone to optical illusions and misinterpretations of sensory data. As a result, He argued that scientists must not rely solely on what they see, but rather verify their observations through objective measurement and experimentation. This skepticism of purely observational knowledge pushed scientific inquiry toward greater precision, ensuring that conclusions were based on measurable and repeatable phenomena. His insistence on repeatability in experimentation was another revolutionary aspect of his work. He believed that a single observation was not enough to establish truth. Rather, an experiment must be repeated under different conditions to confirm its validity. This principle became a cornerstone of the scientific method, ensuring that discoveries were not based on coincidence or subjective bias. His work in optics, in particular, demonstrated this commitment, as he conducted numerous experiments to test how light interacted with various surfaces and mediums. ALHAZEN's approach also integrated mathematics as a tool for scientific proof. He believed that the laws governing natural phenomena could be described using mathematical principles, a belief that placed him ahead of his time. By applying geometric models to the behavior of light, he was able to formulate theories that not only explained optical phenomena, but also provided quantitative predictions. This mathematical rigor was a precursor to the methods later used by scientists such as Galileo and Newton. Another remarkable aspect of ALHAZEN's scientific philosophy was his willingness to admit errors and revise his conclusions when new evidence emerged. In an era when many scholars sought to defend their theories at all costs, he was unafraid to acknowledge when an experiment contradicted his expectations. This humility in the face of evidence set a powerful example for later scientists, reinforcing the idea that scientific progress depends on an openness to correction and refinement. Despite the constraints of his time, ALHAZEN's pioneering methods spread beyond his immediate sphere of influence. His works were translated into Latin in the 12th century, influencing European thinkers who were beginning to emerge from the intellectual stagnation of the Middle Ages. The seeds of his ideas, planted in the Islamic Golden Age, would later blossom into the scientific revolution that reshaped the modern world. Among ALHAZEN's many contributions to science, none was as influential as his monumental work, Kitab al-Manar, commonly known as the Book of Optics. Written over a period of years during his seclusion in Egypt, this 7-volume treatise laid the foundation for modern optical science. Unlike earlier scholars who relied primarily on philosophical speculation, ALHAZEN conducted meticulous experiments to understand the behavior of light, vision, and reflection. His discoveries in these areas would later shape the fields of physics, medicine, and even art. One of the most groundbreaking aspects of the Book of Optics was its refutation of the ancient Greek theory of vision, particularly the ideas of Ptolemy and Euclid. The prevailing belief at the time was that sight occurred because the eyes emitted rays of light that illuminated objects. This emission theory had been accepted for centuries, despite its logical inconsistencies. ALHAZEN, however, was unconvinced. Through a series of carefully designed experiments, he demonstrated that light does not originate from the eye, but rather travels from external sources and enters the eye, leading to perception. To support his theory, he conducted studies on how light behaves when it strikes different surfaces. He observed that light moves in straight lines, and that its behavior changes when it interacts with transparent materials like water and glass. This led him to investigate the principles of reflection and refraction, phenomena that had been vaguely understood before but never systematically examined. He measured the angles at which light was bent when passing through different media, formulating principles that would later influence Renaissance scientists like Johannes Kepler and René Descartes. A major contribution to the Book of Optics was ALHAZEN's explanation of the camera obscura phenomenon. He described how light entering a small aperture in a dark room projects an inverted image of the outside world onto the opposite wall. This principle, though simple in concept, was fundamental to the development of optics and would later be instrumental in the creation of the modern camera. His study of the camera obscura was one of the first recorded investigations into the nature of image formation, an insight that would shape future explorations into visual technology. Another revolutionary aspect of his work was his detailed study of the human eye. Unlike earlier scholars who relied on abstract descriptions, ALHAZEN dissected animal eyes to understand their structure. He correctly identified the cornea, lens, retina, and optic nerve, proposing that vision occurs when light enters the eye and is focused onto the retina. This was a radical departure from previous models, which lacked anatomical accuracy. His research on the eye later influenced European scientists like Leonardo da Vinci and Johannes Kepler, who built upon his findings to develop more precise optical theories. Beyond physics and biology, the Book of Optics also explored the psychological and perceptual aspects of vision. ALHAZEN was one of the first scholars to recognize that the brain plays a crucial role in interpreting visual information. He proposed that perception is not merely a passive reception of light, but an active cognitive process in which the brain reconstructs images based on sensory input. This insight foreshadowed later developments in psychology and neuroscience, centuries before these fields formally emerged. ALHAZEN also studied optical illusions, recognizing that the human mind can be deceived by the way light interacts with objects. He conducted experiments to determine how the position, distance, and shape of objects affect their appearance to an observer. His work in this area laid the groundwork for future studies on perspective, which would later revolutionize art and architecture during the Renaissance. By demonstrating that vision is a complex interaction between light, the eye, and the brain, he moved beyond the simplistic models that had dominated previous thought. The impact of the Book of Optics was profound. When it was translated into Latin in the 12th century, it became one of the most widely studied scientific texts in medieval Europe. Scholars such as Roger Bacon, Whitlow, and Kepler relied heavily on ALHAZEN's findings, using them as a basis for their own research. His experiments and mathematical formulations provided a foundation for future optical advancements, including the development of eyeglasses, telescopes, and microscopes. Despite the depth of his insights, ALHAZEN remained humble about his work. He emphasized that science is an ongoing process of inquiry and refinement, stating that no single theory should be accepted without rigorous testing. His insistence on empirical verification, mathematical analysis, and the systematic recording of observations made the Book of Optics a pioneering work in scientific methodology. His legacy was not only in the discoveries he made, but in the way he transformed the study of optics into a structured and testable discipline. While ALHAZEN is most renowned for his groundbreaking work in optics, his contributions to mathematics were equally significant. He was not merely a theorist, but a problem solver, using mathematical principles to explore the mysteries of the natural world. His approach to mathematics was rigorous and methodical, emphasizing logical reasoning, geometric proofs, and the application of algebra to physical phenomena. In many ways, he built upon the foundations laid by Greek mathematicians such as Euclid and Archimedes, refining their methods while introducing his own innovations. One of his most notable achievements in mathematics was his work on geometry and number theory. He tackled complex problems involving circles, spheres, and parabolas, expanding upon the classical theories of conic sections. His studies in these areas were instrumental in understanding light reflection and refraction, as they provided the necessary mathematical framework to describe how light travels through different media. By combining geometry with empirical experimentation, he was able to derive formulas that explained optical behaviors with remarkable accuracy. In addition to geometry, ALHAZEN made significant advances in algebra. His work helped bridge the gap between the abstract formulations of algebra and their practical applications. He applied algebraic methods to solve geometric problems, an approach that anticipated the later development of analytic geometry. His contributions in this area influenced mathematicians such as Omar Khayyam and, later, European scholars like René Descartes. Through his innovative use of equations, he demonstrated how mathematical abstractions could be used to describe real-world phenomena. One of his most famous mathematical problems was the ALHAZEN's problem, which involves determining the point on a spherical mirror where light from a given source will be reflected to an observer's eye. This problem, deeply rooted in optics and geometry, was extraordinarily complex and remained unsolved for centuries after his time. It was not until the development of calculus in the 17th century that a complete solution was found. The fact that ALHAZEN formulated such a sophisticated problem demonstrates his advanced understanding of mathematical principles and their application to physical science. Beyond specific problems, ALHAZEN contributed to the development of calculus-like methods. Although full-fledged calculus would not emerge until centuries later, his use of infinitesimals and limits in mathematical proofs foreshadowed the techniques later formalized by Newton and Leibniz. His exploration of summation formulas and infinite series showcased his ability to think beyond the constraints of his era, pushing mathematical knowledge toward new horizons. ALHAZEN's work in mathematics was deeply intertwined with his interest in astronomy. He conducted extensive studies on celestial mechanics, using geometric models to describe the movements of planets and stars. He criticized and refined Ptolemy's astronomical theories, pointing out inconsistencies in the prevailing geocentric model. Though he did not propose a fully heliocentric alternative, his mathematical critiques laid the groundwork for later astronomers, such as Copernicus and Galileo, who would ultimately challenge the Earth-centered universe. One of his remarkable achievements was his study of the concept of infinity. While many scholars of his time avoided discussing infinity due to its abstract nature, ALHAZEN explored its mathematical properties with logical precision. His work on the infinite divisibility of numbers and geometric figures influenced later developments in mathematical analysis, showing a profound understanding of concepts that would later become fundamental to modern mathematics. His contributions extended beyond pure mathematics and into the realm of applied mathematics, particularly in engineering and physics. He explored mechanical problems such as the equilibrium of forces, the center of gravity, and the principles of motion. His studies in these areas anticipated key ideas in Newtonian physics, demonstrating the interconnectedness of mathematical reasoning and physical science. Through his detailed calculations, he laid the foundation for later advancements in mechanics and engineering. Another area where ALHAZEN's mathematical insight proved invaluable was architecture and engineering. His understanding of geometric principles helped refine the construction of arches, domes, and other architectural structures. His work influenced builders and engineers in the Islamic world, where geometric precision was essential for designing mosques, palaces, and irrigation systems. His mathematical models provided a more structured approach to architectural planning, ensuring stability and symmetry in large-scale constructions. While ALHAZEN is primarily celebrated for his contributions to optics and mathematics, his work in astronomy played a crucial role in advancing humanity's understanding of the cosmos. At a time when astronomical knowledge was heavily influenced by Greek and Ptolemaic traditions, he introduced a more rigorous, empirical approach that challenged long-held assumptions. His keen analytical mind and reliance on mathematical precision allowed him to identify flaws in existing models and propose refinements that would influence later astronomers. ALHAZEN was deeply critical of the Ptolemaic system, which depicted the Earth as the center of the universe with celestial bodies moving in complex epicycles. While this model had been widely accepted for centuries, ALHAZEN found several inconsistencies within Ptolemy's theories. He examined the mathematical descriptions of planetary motion and pointed out errors in the way the system accounted for irregularities in the movement of planets. His critiques did not go unnoticed. Centuries later, they would provide a foundation for astronomers like Nicholas Copernicus, who ultimately challenged the geocentric model. One of ALHAZEN's most notable astronomical works was Doubts on Ptolemy, in which he systematically analyzed the weaknesses of Ptolemaic astronomy. Unlike many scholars of his time, who simply accepted Ptolemy's model as definitive, ALHAZEN insisted that scientific theories should be scrutinized and tested. His work did not outright reject the geocentric model, but rather questioned its mathematical inconsistencies, setting the stage for future revisions in celestial mechanics. Beyond critiquing existing models, ALHAZEN made significant contributions to the study of planetary motion. He investigated the apparent movement of celestial bodies, analyzing how light and atmospheric conditions influenced human observations of the stars. He understood that the Earth's atmosphere could distort the appearance of celestial objects, a concept that later astronomers would explore further in their studies of atmospheric refraction. His observations helped explain why stars appear to twinkle and why the sun and moon seem distorted when near the horizon. One of Alhazen's most remarkable insights was his study of the nature of light in space. He theorized that celestial bodies did not emit light in the same way as terrestrial objects, but instead reflected and refracted light in complex ways. This idea was particularly relevant to the moon, which he correctly identified as a non-luminous body that reflects sunlight. His work in this area contributed to later understandings of planetary albedo and the way light interacts with celestial surfaces. His mathematical expertise also extended to astronomical instruments, where he played a key role in improving observational tools. He refined the design of the astrolabe, an ancient device used to measure the positions of stars and planets. By introducing more precise measurement techniques, he enabled future astronomers to obtain more accurate data on celestial movements. These advancements were crucial in the development of Islamic and later European astronomy, allowing for better navigation and celestial mapping. Alhazen's contributions also extended to lunar and solar studies. He conducted detailed observations of lunar eclipses, using mathematical calculations to estimate the distance between the Earth and the Moon. His work in this area anticipated later discoveries about the size and scale of celestial bodies. Similarly, he studied solar eclipses, making careful notes on the behavior of light and shadows during these rare events. His descriptions of the way sunlight bends when passing through the Earth's atmosphere were remarkably advanced for his time. Another key area of his research was the nature of time and celestial cycles. He explored the movements of the sun, moon, and planets in relation to the Earth, attempting to refine calculations of timekeeping. His work contributed to the accuracy of astronomical calendars, which were essential for determining religious observances, agricultural cycles, and navigation. The precision of Islamic astronomy during the medieval period owed much to scholars like Alhazen, whose mathematical and observational rigor improved timekeeping techniques. Perhaps most importantly, Alhazen's approach to astronomy embodied the principles of empirical science. Rather than blindly following ancient texts, he emphasized observation, measurement, and mathematical verification. His insistence on testing theories through experiment and calculation helped establish astronomy as a more precise and quantitative science. This methodological shift was a precursor to the later scientific revolution, where empirical inquiry became the standard approach to understanding the universe. Beyond his mathematical and scientific achievements, Alhazen was also deeply engaged in philosophy and theology, exploring the nature of knowledge, perception, and truth. Unlike many scholars of his time, who were either strict adherents of religious doctrine or pure rationalists, Alhazen sought a harmonious balance between faith and reason. His philosophical inquiries were grounded in a deep intellectual curiosity, and his writings reflected an effort to reconcile scientific inquiry with theological principles. A central theme in Alhazen's philosophical work was the pursuit of certainty in knowledge. He was deeply concerned with the reliability of human perception and the limitations of the senses. He understood that the senses could be deceived, whether through optical illusions or psychological biases, and thus emphasized the importance of empirical verification. This perspective led him to argue that true knowledge must be obtained through systematic investigation rather than through passive acceptance of inherited beliefs. Alhazen's skepticism toward untested knowledge extended to his critique of philosophical traditions. While he respected the works of Aristotle and other ancient thinkers, he did not accept their conclusions blindly. Instead, he believed that all claims, whether philosophical, scientific, or religious, should be examined critically. His approach contrasted with the prevailing intellectual climate, which often treated ancient authorities as unquestionable. In this way, he anticipated later scientific skepticism, advocating for a method of inquiry that valued evidence over tradition. His work in optics, particularly his studies on light and vision, had profound philosophical implications. He proposed that what humans perceive is not always an accurate representation of reality, but rather a mental reconstruction based on sensory input. This idea foreshadowed later debates in epistemology regarding the nature of perception and the extent to which the mind shapes human understanding of the world. His insights into the subjective nature of vision were revolutionary, challenging the assumption that seeing is equivalent to knowing. In addition to his scientific skepticism, ALHAZEN engaged with metaphysical questions about existence and causality. He explored the nature of the physical universe, contemplating whether the laws governing light and motion were evidence of a higher order. Though he operated within an Islamic intellectual framework, his approach was not purely theological. Rather, he sought to understand the divine through the study of natural phenomena. He saw scientific inquiry as a means of uncovering the underlying principles of creation, an idea that resonated with later thinkers in both the Islamic and Western traditions. One of ALHAZEN's key theological contributions was his discussion on the role of reason in religious belief. While he maintained a strong faith in God, he argued that religious truths should not contradict reason. He believed that the study of the natural world could enhance one's understanding of divine wisdom, rather than diminish it. This perspective aligned with the broader intellectual movement of Islamic rationalism, which sought to integrate logic and faith in a way that encouraged knowledge and discovery. His philosophical outlook also extended to ethics and the responsibilities of scholars. He believed that intellectuals had a duty to seek truth and to share their findings honestly, regardless of personal or political consequences. He criticized scholars who distorted knowledge for personal gain or who blindly followed authority without questioning it. His belief in the integrity of knowledge production set a precedent for later scientists and philosophers, reinforcing the idea that truth must be pursued for its own sake. ALHAZEN's rationalist approach influenced subsequent Islamic philosophers, including Averroes, Ibn Rushd, and Avicenna, Ibn Sina, both of whom integrated his ideas into their own works on logic and metaphysics. His emphasis on empirical investigation also played a role in shaping the intellectual climate of medieval Europe, where his works were studied alongside those of classical Greek philosophers. His impact on Western thought was particularly evident during the Renaissance, when scholars began to re-emphasize the importance of observation and reason in both science and philosophy. Despite his scientific rigor, ALHAZEN was acutely aware of the limitations of human knowledge. He acknowledged that while empirical investigation could reveal much about the natural world, there were mysteries that lay beyond human comprehension. This humility in the face of the unknown set him apart from more dogmatic thinkers of his time. He recognized that science was an ongoing process and that future generations would continue to refine and expand upon his discoveries. ALHAZEN's contributions to knowledge were not merely confined to his own time. They rippled through history, influencing scholars, scientists, and intellectuals for centuries. His meticulous methods, empirical approach, and mathematical precision established a new paradigm for scientific inquiry. He was more than a mathematician, physicist, and philosopher. He was a visionary whose ideas reshaped how humanity pursued knowledge. From the Islamic Golden Age to the European Renaissance and beyond, his influence endured, inspiring generations of thinkers to challenge assumptions and seek the truth through observation and reason. One of ALHAZEN's most enduring impacts was his role in shaping the scientific method. Long before Francis Bacon and René Descartes formalized modern scientific inquiry, ALHAZEN had already demonstrated the importance of experimentation, hypothesis testing, and logical reasoning. His insistence on empirical evidence over pure speculation laid the foundation for a more rigorous and systematic approach to science. The methodologies he developed for optics became a model for future researchers, influencing disciplines far beyond physics. His groundbreaking work in optics, particularly his Book of Optics, was translated into Latin and became a cornerstone of European scientific study. During the Renaissance, his insights were studied by key figures such as Roger Bacon, Johannes Kepler, and Galileo Galilei, who built upon his findings to advance the understanding of light, vision, and the movement of celestial bodies. Without Alhazen's meticulous work on refraction, lenses, and optical principles, the development of modern optics, including telescopes and microscopes, would have been significantly delayed. Beyond optics, his influence extended into mathematics, astronomy, and engineering. His application of algebraic principles to geometry anticipated the development of analytic geometry, a key concept that later influenced both Newton and Descartes. His critiques of the Ptolemaic system contributed to the eventual paradigm shift toward the heliocentric model, even though he himself did not explicitly propose it. His explorations of mechanical systems and equilibrium laid the groundwork for later advancements in physics, particularly in understanding forces and motion. Alhazen's impact was not limited to the scientific community. His emphasis on rational inquiry and skepticism of unquestioned authority played a role in shaping philosophical thought in both the Islamic world and Europe. His method of scrutinizing ancient texts, including revered works by Aristotle and Ptolemy, encouraged later scholars to apply the same level of critical analysis to all areas of knowledge. His legacy helped foster an intellectual culture in which reason, rather than tradition, became the primary tool for understanding the world. His work also contributed to technological advancements. His optical theories directly influenced the development of eyeglasses, improving vision for millions. Later applications of his principles in light and reflection led to advancements in photography, cinematography, and even fiber optics. His studies of architectural geometry and structural stability contributed indirectly to engineering and construction methods, demonstrating how abstract scientific concepts could have real-world applications. Despite his immense contributions, Alhazen remained a largely humble and underappreciated figure for many centuries. While his works were widely studied in medieval Europe, his name was often overshadowed by later scholars who built upon his discoveries. However, modern historians of science have begun to reevaluate his legacy, recognizing him as one of the most important scientific minds of the medieval era. His work is now acknowledged as a critical bridge between ancient Greek knowledge and the scientific revolution of early modern Europe. Today, Alhazen is celebrated as a pioneer of interdisciplinary thought, blending physics, mathematics, philosophy, and theology into a cohesive pursuit of knowledge. His ability to navigate multiple fields and make profound contributions to each is a testament to his intellectual versatility. In an age where specialization often dominates academia, his example serves as a reminder of the power of cross-disciplinary thinking and the importance of seeking connections between different branches of knowledge. His legacy also carries a powerful message about the universality of science. Though he lived in the Islamic world during the medieval period, his ideas transcended cultural and religious boundaries, influencing scholars across civilizations. His work exemplifies the notion that scientific progress is a cumulative endeavor, built upon the contributions of diverse cultures and generations. His story underscores the importance of preserving and sharing knowledge, ensuring that future discoveries are not lost to history. Ultimately, Alhazen's life and work stand as a testament to the enduring power of human curiosity and reason. His relentless pursuit of truth, his rigorous methodology, and his willingness to challenge established dogma made him a transformative figure in the history of science. As long as humanity continues to seek knowledge and question the nature of reality, Alhazen's legacy will remain alive, a guiding light for those who, like him, dare to explore the unknown.